A commercial flooring specification sheet acts as a preventative structural matrix. It establishes the rigid physical boundaries required to mitigate mechanical failure in high-traffic environments. We will use Moldart as our primary case study to examine the tolerances and performance limits expected of commercial-grade materials. We are looking past surface aesthetics to analyze the specific physical parameters that distinguish standard medium-density fiberboard from high-performance high-density fiberboard, or HDF. Long-term field performance is supported by three distinct pillars: internal mechanical integrity, moisture defense, and strict subfloor calibration. The process begins with raw wood fibers. These must be chemically and physically compressed to achieve exact European norm standards for density and strength. Understanding these pillars allows specifiers to predict and prevent structural failure before a single pallet of material arrives at a job site. This technical specification sheet provides the required structural benchmarks for our analysis of high-performance HDF. Every numerical row in this document represents a calculated defense against a specific mechanical or environmental failure mode. This table identifies the density metric, establishing a target of 850 to 1,040 kilograms per cubic meter to satisfy the EN 323 standard. Shifting down the document, we find the modulus of elasticity and bending strength requirements, mandated by the EN 310 standard. These values serve as the structural map for deconstructing the physical reality behind the material's performance. Failing to interpret this spec sheet accurately leads to a catastrophic misalignment between the engineered core and its intended environment. Within the microscopic internal matrix, a density of 850 to 1,040 kilograms per cubic meter is the mandatory baseline for commercial durability. This density ensures the core withstands localized compression from heavy traffic. Density is supported by chemical bonding. Internal bond strength, 1.2 newtons per square millimeter, locks fibers together under stress. If inadequate, the joint suffers catastrophic delamination, splitting under pressure. This specific mechanical failure mode is known as zippering, and it is the primary threat to the longevity of commercial flooring. Density provides the mass, but internal bond strength provides the active structural integrity to prevent zippering. Moving from the joint to the macroscopic span of the board, we evaluate the modulus of elasticity, benchmarked at 3,500 newtons per square millimeter. MOE measures stiffness, calculating how well the material resists elastic deformation over gaps in the subfloor. Bending strength, or MOR, must exceed 40 newtons per square millimeter. This determines the board's ability to resist fracturing under tension. Because minor subfloor variations are physically inevitable, these EN 310 metrics dictate how well the floor handles those imperfections. Standard MDF cannot meet these requirements. Inferior materials would permanently sag or snap when subjected to the same bridging forces. MOE and MOR are the literal safety margins that keep the floor intact over imperfect concrete. The substrate's greatest external vulnerability is environmental moisture, which is governed by the EN 317 thickness swell standard. While standard allowance is less than 18% volume swell, premium HDF requires a much tighter tolerance of less than 10% expansion after 24 hours of exposure. High humidity and coastal regions act as primary threat vectors that can easily overwhelm standard swell tolerances. To counter this, factory-applied hydrophobic wax sealants are used to repel liquid water at the material's most vulnerable points. This wax must be applied to all 4 click-lock profiles to prevent moisture from penetrating the microscopic gaps in the seams. If moisture successfully enters the joint, it triggers a destructive failure mode known as edge paking, where the seam expands upward. Without these chemical defenses at the joint profile, the mechanical integrity of the entire HDF matrix is compromised. On the macroscopic level, the locking profile must be calibrated to the specific scale and installation speed of the project. The Uniclick system is specified for large spans over 20 meters, utilizing active mechanical tension to pull horizontal seams tight. In contrast, the Valengay 5G system uses a drop lock mechanism engineered for rapid commercial installation, prioritizing vertical locking stability. Moving from the core to the surface, high-definition textures require heavy industrial tooling. To maintain pattern consistency over massive production runs, stainless steel press plates with a surface hardness of 65 to 70 HRC must be utilized. This surface engineering determines the EN 13329 abrasion class, ranging from AC3 for residential use to AC4 and AC5 for heavy commercial traffic. Every specified feature, from surface hardness to locking tension, is an engineered response to a distinct field condition. Beyond the engineering of the HDF board itself lies the foundation it rests upon, the ultimate environmental fail point. Concrete subfloors must not exceed a moisture vapor emission rate of 3 pounds per 1,000 square feet over a 24-hour period. A 6 ml polyethylene vapor barrier is mandatory to block rising vapor and protect the substrate from saturation. Omitting this barrier voids the manufacturer warranty and nullifies the material's internal engineering. Even the highest wear ratings and strict mechanical tolerances depend entirely on this final stage of installation preparation. The engineering of the substrate provides the mechanical potential, but the survival of the floor is ultimately governed by the environment in which it is placed.